You've probably heard that liquids are incompressible, right? You push on water and it doesn't shrink. But that's not exactly the whole story. Turns out, fluids have this kind of hidden stiffness that is absolutely crucial for everything from the brakes in your car to massive, heavy-duty construction equipment. So let's dive in and figure out what that really means. To get our heads around this, let's start with a really simple question. You know this from experience, right? You can take an empty soda can and crush it with your hands, no problem. But try doing that to a sealed plastic bottle that's completely full of water. Yeah, good luck. It's basically impossible. So what is going on there?
Well, it all comes down to the molecules. In a gas, like the air in that can, the molecules are just floating around, really far apart. There's tons of empty space between them. It's kind of like a few people scattered around a giant empty room. It's super easy to push them closer together. But in a liquid, those molecules are already packed in there, shoulder to shoulder, like a sold-out concert. There is almost zero empty space left, so you just can't squeeze them any closer.
Okay, so we get the idea that liquids are stiffer than gases. That feels right. But in science and engineering, a gut feeling isn't going to cut it. We need to move past that and put a real number on this property. So how do we actually measure this stiffness? That number is called the bulk modulus, and that's the key concept for this whole explainer. You can literally think of it as a fluid's stiffness rating. A really, really high bulk modulus means the fluid is incredibly resistant to being compressed. A low bulk modulus means it's much more, well, squishy, like a gas. And hey, this isn't just a loose analogy I'm throwing out there. The scientific literature defines it crystal clear. This quote from a major survey on the topic says it all. It is the direct measure of a liquid's resistance to compression. In other words, it's the exact opposite, the reciprocal of compressibility. Okay, now here's where things start to get really, really interesting. You might be thinking, great, one number, the bulk modulus, I got it. Well, hold on, it's not that simple. Turns out, depending on how you measure it, you can get 4 different values for the bulk modulus of the exact same fluid. Just take a look at this graph. It shows what happens to a fluid's volume as you crank up the pressure. And as you can see, it's not just one clean, simple line. Each of these curves represents a different way to measure that stiffness, and they give you different answers. This proves it's not just some single fixed property. So what are these different ways? Well, the first big distinction comes down to one thing: speed. If you compress a fluid super slowly, any heat that's generated from the squeezing has time to escape, and the temperature stays the same. That's what we call isothermal. But if you compress it really fast, bam, the heat gets trapped. That temperature increase actually pushes back against you, making the fluid seem even stiffer than it really is. That's called adiabatic. All right, that's speed. The other piece of the puzzle is all about how we do the math. Are we measuring the stiffness at one single, precise, instantaneous moment of pressure? That's the tangent bulk modulus. Or are we calculating the average stiffness across a whole range of pressure, say from 0 all the way up to 1,000 psi? That's the secant bulk modulus. Okay, but let's be real. Does all this actually matter? Are we just splitting hairs here? Oh yeah, it matters a lot. Just look at the numbers for a typical hydraulic oil. The isothermal secant value is 1.88 gigapascals, but the adiabatic tangent value is 2.41. That is a difference of over 25%. So yeah, if you're an engineer designing a system, choosing the wrong one could be a massive mistake. But now we get to the real villain of the story. Because all those factors we just talked about, pressure, temperature, how you measure it, they all get completely overshadowed by one single thing that can absolutely sabotage a fluid's stiffness. That's right. The single biggest, most disruptive factor has nothing to do with an inherent property of the fluid itself. It's an invisible intruder, a contaminant that can sneak into almost any hydraulic system and just wreck the whole thing. And that villain is air. But not all air is the same. You can have dissolved air, which is harmless, just individual molecules mixed in. You can have big pockets of free air, which isn't great, but you can usually bleed it out of the system. The real bad guy, the one we have to worry about, is entrained air. Tiny, microscopic bubbles whipped into the fluid, almost like foam. So how bad is it? Get ready for this. At a pretty low pressure, if just half of 1% of your fluid's volume is made of these tiny air bubbles, it will cut the bulk modulus, the stiffness, in half. 50% gone. The fluid becomes twice as compressible. That isn't just a change, that is a catastrophic failure. So, let's pull all of this together and connect it back to the real world. Why should you care about this hidden stiffness, and especially about this bubble problem? Why does it matter so much for everything from giant construction machines to the very brakes that stop your car?
When a hydraulic fluid gets too spongy, it's a disaster waiting to happen. You immediately start losing power because your energy is just wasted squeezing the fluid instead of doing work. You can get something called cavitation, where those tiny bubbles collapse with so much force they can literally eat away at solid metal parts. And maybe the most dangerous part, when a highly compressed, spongy fluid suddenly decompresses, it releases all that stored energy in a violent shockwave. It's like a bomb going off inside your machinery.
This is also why engineers have to make really tough choices about what fluid to use. Believe it or not, water actually has a very high bulk modulus, making it one of the stiffest common liquids out there. But, it rusts things. Oil is a bit less stiff, but it's a fantastic lubricant and protects all the metal components. So it's always this trade-off between the fluid's stiffness and all its other vital properties. So the next time you see one of those giant excavators or a massive crane effortlessly lifting literal tons, remember what's happening inside. All of that immense power is balanced on the idea that the fluid inside is perfectly, absolutely stiff and incompressible. And the question I want to leave you with is this. What happens to all that power, all that stored energy, when the fluid holding it all together suddenly isn't?